Key quantities important for DAC performance include 1. Quantization noise represents the uncertainty introduced when converting analog values into discrete digital levels, inherent to finite resolution. 2. Dynamic range, DR the ratio of the full-scale range, FSR, to the smallest resolvable difference, 1 LSB. It reflects the DAC's ability to handle signals over a wide range of amplitudes. 3. Signal-to-noise ratio, SNR the ratio of the full-scale value to the root mean square, RMS, of quantization noise. It measures the quality of the output signal relative to noise. 4. Effective number of bits, ENOB, indicates the actual resolution of the DAC, derived from the observed SNR, factoring in real-world non-idealities. 5. SNR actual, the observed signal-to-noise ratio in practice, which may differ from the theoretical ideal due to imperfections in the DAC design. These metrics collectively define the precision, accuracy, and performance of a DAC. Quantization noise refers to the error or uncertainty introduced when an analog signal is digitized by a finite-resolution converter, such as a DAC or ADC. Since the converter maps a continuous range of analog values to discrete levels, the difference between the actual analog value and the nearest discrete level results in this noise. Quantization noise is inherent to the conversion process and limits the precision of the digital representation. Dynamic range, DR, is a key metric of a DAC, representing its ability to handle signals over a wide range of amplitudes. It is defined as the ratio of the full-scale range, FSR, of the DAC to its smallest resolvable difference, which corresponds to one least significant bit, LSB. Mathematically, it is expressed as dynamic range, DR, is equal to FSR divided by LSB. This ratio highlights the precision of the DAC, indicating how effectively it can distinguish between small changes in input values while accommodating the full range of possible outputs. The signal-to-noise ratio, SNR, of a DAC is the ratio of the full-scale output value to the root mean square, RMS, value of the quantization noise. The RMS value of the quantization noise is calculated by determining the root mean square of its amplitude. For the quantization noise represented by the solid line, this calculation yields the corresponding SNR. The effective number of bits, ENOB, is derived from the signal-to-noise ratio, SNR, and quantifies the actual resolution of a DAC. It reflects the number of bits the DAC effectively uses to represent the output signal, accounting for noise and non-idealities. Mathematically, it can be expressed as ENOB is equal to SNR minus 1.76 divided by 6.02. This formula connects the observed SNR to the DAC's performance, indicating its true precision in practical applications. Figure explanation. A. Offset error. Offset error occurs when the output of a DAC is consistently shifted from the ideal characteristic by a fixed amount across all input values. This results in the output starting at a value higher or lower than the expected origin, as shown in the figure. It represents a horizontal shift in the transfer curve of the DAC. B. Gain error. Gain error refers to a deviation in the slope of the DAC's output characteristic from the ideal slope. This error causes the output to differ proportionally with the input, leading to either a higher or lower output across the range. It represents a scaling error, affecting the magnitude of the output values relative to the input. These errors highlight imperfections in the DAC and are critical to understanding its static performance. Figure explanation. Integral nonlinearity, INL measures the deviation of the actual output of a DAC from the ideal straight line characteristic. It reflects cumulative errors across multiple codes and indicates how much the DAC output strays from the expected trajectory. Differential nonlinearity, DNL measures the difference between the actual step size of the DAC output and the ideal step size, 1 LSB. If the DNL exceeds plus or minus 1 LSB, it can result in missing codes, meaning certain output levels are skipped entirely. Non-monotonicity. Non-monotonicity occurs when the DAC output does not consistently increase or decrease with increasing input codes. This results in a reversal or drop in the output, which can disrupt critical applications requiring smooth transitions. These characteristics reveal static imperfections in a DAC's performance and are key parameters for assessing its accuracy and reliability. Differential nonlinearity, DNL, is a measure of the deviation in voltage between adjacent output levels of a DAC. It focuses on the difference between the actual voltage change between successive output codes compared to the ideal voltage change expected for a perfect DAC. DNL measures the bit-to-bit deviation rather than considering the overall transfer function of the DAC. Monotonicity in DACs. A monotonic DAC ensures that as the digital input increases, the analog output never decreases. This property is critical in applications where precise incremental changes are required, avoiding unintended oscillations in the output signal. Equation for the output of the ith bit. The equation shows that the output contribution of the ith bit is proportional as shown in equation, where n is the total number of bits in the DAC. It highlights how higher bits contribute larger values to the analog output compared to lower bits. Accuracy of the ith bit. The accuracy is expressed in terms of the least significant bit, LSB. It shows that the accuracy of each bit decreases exponentially with lower bit positions, making higher bits more critical for overall precision. The accuracy is also represented as a percentage, providing an intuitive measure of its impact on the output. These equations underline the importance of monotonic behavior and bit-specific contributions to the performance of a DAC. Conversion speed, defined as the time a DAC takes to produce a stable analog output after the digital input changes. Conversion speed ranges from milliseconds for slower, higher-resolution DACs to nanoseconds for high-speed applications. Factors influencing speed. Parasitic capacitance, unintended capacitance in the circuit slow down the response time. Op-amp characteristics. Gain bandwidth determines how quickly the op-amp can respond to changes in the input. Slew rate, the maximum rate of change of output voltage. A low slew rate limits the speed of the DAC. Gain error, caused by the finite open-loop gain AVD, 0 _VD, 0 AVD, 0 of the op-amp, leading to deviations from the desired output voltage. Equation for gain error in a DAC using an op-amp. The finite open-loop gain AVD, 0 of the op-amp influences the closed-loop gain. If the closed-loop gain is not ideal, it results in a difference between the expected and actual output, affecting precision and dynamic performance. This slide sets the foundation for understanding how DAC performance depends not just on the converter itself, but also on external components like op-amps and parasitic elements. Using the formula discussed, we calculate the value of gain error first, and then the value of n.